Hello everyone, I'm Andong Wang from Hong Kong U. Today, I will present our work, a multitask ultrasound image analysis model by vision language co-training. Recent advancements in vision language models such as CLIP and GPT-4 have demonstrated the power of large models trained on large datasets. Those models are also called foundation models. Instead of learning something specific, foundation models tend to understand the world as they unify different tasks and are trained on different sources of data. Then, we may wonder, can we train a foundation model for ultrasound image analysis? Currently, we train different small models for different types of images. However, a small model trained to segment left ventricle does not know what left ventricle is. All it has learned is some light patterns and certain textures. For humans, a good sonographer should master different types of ultrasound images. Therefore, a powerful model should integrate different datasets and build the concepts of different organs and tissues. Then, the question becomes how to integrate different datasets. The naive approach is to simply combine all the datasets. But can we do that? When training one small model for one dataset, the model learns the unique visual feature distribution of the image content. For example, the distribution of left ventricle. If we mix different types of images directly, what we do is combining different distributions directly. Literature has shown that the learned distribution would be distorted, and therefore the model performance would drop. To address this challenge, we propose a new approach that employs natural language to condition the model when integrating ultrasound image datasets. This is like when teaching a student. We do not random mix the learning materials and throw them to the student. Instead, we teach the student chapter by chapter. Chapter 1 is left ventricle. Chapter 2 is breast cancer. Chapter 3 is thyroid. With such an organized learning approach, the student can learn much better. Then, the question becomes how to design natural language conditioning. While inspired by recent works such as segment anything and scene, they use prompts to guide the model to do image analysis tasks, like the figure on the top shows. Given an image of scissors, you input text, segment scissors. The model will segment scissors. Therefore, we use prompts as natural language conditioning, like the workflow shows. Users input prompts plus image to the model. For example, please segment and classify breast cancer. The model output is text plus mask. It tells us the breast cancer is malignant and provides the corresponding segmentation of it. Such input and output format is general and user-friendly because different tasks such as segmentation and classification can be unified. And end users can communicate with the model in a natural way. Next is our method. This slide shows the model architecture, which can do both segmentation and classification tasks. Our model is primarily composed of a unit with 5 downsampling and 5 upsampling layers. 4 of those layers incorporate multi-head across-attention modules that integrate image features with prompt embeddings obtained from a frozen clip text encoder. The unit outputs the segmentation result. For classification task, a frozen clip image encoder is concatenated with a head network attached to the last downsampling layer. Output the yellow vector, which contain the semantic information of the classification results. Then, how to decode the yellow vector? We will encode potential choices such as malignant and benign with a frozen clip text encoder and compare the similarity between the yellow vector and embedded choices. Next, we find the yellow vector representing malignant. Such design enables the model to do various classification tasks, regardless of the number of the classes. This slide shows the 10 datasets we used to train our model. The datasets cover various ultrasound image contents, including left ventricle, breast cancer, thyroid, fetal head, cerebral tumor, abdominal organs, and PCOS. We designed prompts for each dataset and integrate the 10 datasets to train our model. This slide shows the experimental results. 7 out of the 10 datasets are for segmentation tasks. Without careful model architecture design and hyperparameter selection, our model achieves comparable performance with existing SOTA methods, while outperforming existing method significantly on the RESEQ dataset, that is the cerebral tumor dataset. Also, our model has comparable performance on the 4 classification tasks. Next, we did an ablation study to prove the effectiveness of using prompts. The blue bar indicates our model, and the green bar indicates the situation where no prompts were used. We can see that there is a 4% and a 1% drop of overall accuracy for segmentation task and the classification task, respectively. The minor drop in overall accuracy is because 2 out of the 10 datasets are much larger than others. Low prompt model learns the 2 dominant datasets, while they may perform badly on small-scale datasets. For example, no prompt model has only 65% dice accuracy on the breast cancer segmentation dataset named BUSI. Also, we can see the significant performance drop of the classification task on both BUSI and abdominal classification dataset. Although the model achieves satisfactory performance, we may wonder why. What does the model learn? Can the model distinguish different organs while building connections between concepts and image features? To answer this question, we use a deep learning interpretation method named HINT to decode the model. Please see the paper for method details. And here I only focus on the objective and the results. So, this is our model. We choose a layer in the red circle as a target. So why we choose this layer? The reason is that the layer is the input to the head network and the bottleneck of the unit. It should contain both vision and somatic features. What we do here is to build the connections between the neurons and the concept and image features. For example, which neurons are responsible for the concept of left ventricle, and which neurons are responsible for the ultrasound image of left ventricle. The results shows that there do exist responsible neurons for both vision and text features of different organs. This slide uses abdominal organs as an example. A group of neurons responds to visual features of liver, while another group of neurons responds to the word liver. Besides, there are some multimodal neurons. For example, neuron 487. It responds to both vision features of liver and the word liver. To conclude, first, the reason we do this work is that a model can have a more comprehensive understanding of ultrasound images by training the model on massive and diverse ultrasound images. However, Directly combining different datasets, combining different ultrasound images, might decrease the model performance. To solve this problem, we propose a simple but effective method by integrating multiple ultrasound image datasets by natural language conditioning. For future work, most importantly, data is a key. We need more diverse, high-quality datasets combining images and texts. Second, current model was built based on CLIP and can only do segmentation and classification tasks. We may incorporate large language models such as Llama to achieve multitasks. Last but not least, you can scan the QR code to check our GitHub and see our demo video. Thanks a lot.